Hogden with us. He's from the Los Alamos National Lab. He might be able to tell you why people are doing speech processing at Los Alamos. I only knew them for making bombs, but perhaps there's a connection. But in any case, let me just take a minute to introduce him. He has a bachelor's degree in psychology from the University of Washington, 1985, I think. And then from there he went on to Stanford, where he did a PhD with David Rumelhart, whom some of you may have heard of. And he worked on cognitive science, psychology, and in particular on speech perception. And so he's been doing speech-related work since then. And he'll tell us today about a particular method of speech signal normalization, which he calls, do you call it Malcolm? Or?
Yeah, okay. I call Malcolm.
Which is called Malcolm.
Well, the reason they're interested in speech at Los Alamos is because I told them that some people in speech study plosives, and they thought that was pretty cool. So I've been doing it ever since then. They haven't quite figured it out. The work I'm going to be presenting was done in collaboration with a graduate student, Patrick Valdez. In fact, he did most of the work. And with a mathematician, Leonid Gurvitz, who I probably wouldn't be able to do very much of this at all without. So I really appreciate those guys' help. I'm basically going to be trying to make 2 points during my talk today. The first point is that we should use articulation, or to try to go from acoustics to articulation as a first part of our speech processing for speech recognition or for a variety of tasks, probably speaker recognition as well. And the second point I'm going to try to make is that we actually can use articulator information. We can do that inversion from acoustics to articulation, and so then should do it. You may believe me or not when I'm done, but that's what I'm going to be trying to say. More specifically, I'm going to start out talking about why we either should or maybe should not use an articulatory representation as a step in our speech processing. And then I'm going to talk about Malcolm, which stands for Maximum Likelihood Continuity Mapping. It's a stochastic model of speech that I use to try to make that inversion from acoustics back to articulation. And in fact, then there's going to be a whole section where I just talk about what Malcolm does. And as far as I'm concerned nowadays, I'm realizing that Malcolm is just a way of inverting nonlinear functions that you cannot directly observe. And the important point I'm going to make there is that I think that we can invert from acoustics back to articulation, even if we're never given articulatory data. And that's kind of an off-the-wall claim, right? Typically, if I told you that we were going to find a nonlinear relationship between x and y, you would say, okay, just give me x and y, I'll do some nonlinear regression, and we'll get that relationship. But I'm actually going to be making the claim that we can do that nonlinear inversion without ever seeing any y data at all. And we'll see whether I can convince you of that. However, I don't think that the output of Malcolm should necessarily be used for speech recognition just as it is. And in fact, I'm going to talk about another algorithm just a little bit if I have time, called co-Malcolm, which is how I envision Malcolm fitting into a speech recognition system. And the important point to make on that is that I think that we'll be able to hook this kind of stuff together with ordinary trellis models like people use right now for word models or phonemes given words, those kinds of things. Now, when I was a graduate student, there were important reasons to believe that I was completely wasting my time in trying to get back articulated position from acoustics. In fact, at the time, we knew very well it was impossible to recover articulated positions from acoustics, so obviously it was a waste of time to try to do it. However, we knew that at the time because of simulations of the vocal tract. And in fact, those simulations would often show us that, for example, the tongue could move 2 centimeters without changing the formant frequencies, the first 3 formant frequencies at all, and without changing the bandwidth of a formant frequency by even 1 hertz. Right? That's an incredible amount of variation in the tongue. In fact, it's so incredible that you really should take that word incredible in its literal form. It's really unbelievable. And as a matter of fact, nowadays, we can easily measure articulator positions and their motions. And when people have done research where they just have measured articulator positions, and they have acoustics as well, and they try to do really simple approaches to inverting from acoustics back to articulation, in fact, they get back tongue positions to within about a millimeter and a half. So we're seeing an order of magnitude better recovery in reality than what was predicted by some of the simulations and mathematical work. I have to be a little bit careful when I talk about the simulations, because in fact there are a variety of simulations done, and just the tiniest little changes in the assumptions underlying the simulations can lead to an order of magnitude difference in the results as well. So in fact, it's not clear to me now why we knew so for sure back then that you could not recover articulator positions when even the simulations were varying by an order of magnitude. How do you choose which ones to believe? Another good reason to not recover articulator positions was that if we did that, we were going to have to do extra processing to the acoustics. And if we did that, we were going to lose information. Why in the world would we do more processing to throw away information from the speech signal and obviously make our recognition results worse? Well, that actually is kind of a tenuous argument. In fact, it's contradictory to this first one. Right? If you believe that there's a many-to-one mapping, many different articulator positions can produce the same acoustics, then what you must be believing is that, in fact, there's more information in the articulator motions than in the acoustics. Right? We've lost information through that many-to-one mapping. And in fact, there's got to be at least some many-to-one mapping, because every articulator position that I want to use can produce silence. Watch. Right? I can produce silence in all kinds of different ways, right? So there's at least that many-to-one mapping. But if we could use, for example, dynamic information to infer articulator positions given some constraints, there's actually more information in the acoustics or in the articulation than in the acoustics. So actually, I don't believe that argument holds a lot of water. In fact, I think there are a lot of reasons that you might want to use articulator positions instead of acoustics. Not just the argument about information. So, for example, these are what I call the manifolds of speech. This set of blue points over here is supposed to represent all of the possible articulator positions of some hypothetical vocal tract. Now, obviously, a vocal tract has more than two parameters, two freely varying parameters. So here I showed tongue fronting and tongue height, but you know, there's tongue tip position, jaw position, lip position, a variety of different things. In reality, this space here would have to be multidimensional and probably wouldn't even be blue. This, this red trajectory here is supposed to show you a trajectory through the articulator path, or through the articulator positions. And notice that I drew it very smoothly. And in fact, if we look at articulator motions, just measured motions, and we do a Fourier transform of them, we find they have almost no energy above, say, 8 or 15 hertz, depending on what you want to use as a cutoff. So in fact, articulator motions are very smooth. However, if we take that space and convert each of these articulator positions into an acoustic signal, however you want to measure it, we're going to be doing some kind of transformation of that. So for example, over here I said, well, what if we used Melchepster 1 as one axis in the acoustic space, Melchepster 2 as another axis, Melchepster 3 here, 4 out in some other dimensions, say we have 30 or 40 different Melchepstra axes here, then we can say something about what this manifold over here looks like. In fact, it's going to be this set of positions, however many dimensions it is, contorted and embedded in some higher dimensional space. The dimensionality of the space is not going to increase. If we have 2 dimensions in our articulator trajectory and we use 30 dimensions over here in the acoustic space, what we're really going to have is a 2-dimensional surface just contorted and stuck over here in acoustics. And that gives you some reason for pause when you think about what we do as the first step of most kinds of acoustic-based speech processing. What we often do as the first step is to place some probability density function over the acoustic space. So for example, we'll put a Gaussian or a mixture of Gaussians over this acoustic space to try to estimate the probability of the different acoustic signals. Well, we've got to think a little bit about what we're doing then. If we take a 30-dimensional Gaussian and try to use it to cover a, I don't know, 8-dimensional space, for example, then clearly most of the Gaussian is not even on the manifold. And this is all the possible acoustic signals that can be produced by this set of articulator positions, right? Now, there are some acoustic signals that can be off of this manifold here. Those are the signals that are caused by noise. So if I have a 30-dimensional Gaussian sitting over this space, then maybe 8 parameters at that, of the covariance matrix, for example, have to do with actual sounds that can be produced by articulation. And all the rest of the parameters are trying to approximate the noise environment in which we're doing our recognition. That's a problem, right? When the noise environment changes, all of a sudden our parameters are not accurate anymore, and that could lead to reduced performance in recognition. Furthermore, Notice that I did not draw that path as smooth over here. And in fact, we know that the trajectories through the acoustic space are going to have very high frequency components in them. So suppose you wanted to use context to try to give back information about the sound that you missed. Right? Suppose you have noise in your signal, you missed sound, you want to use context. Over here in articulator space, if I have noisy data, I use a really simple procedure to get rid of the noise. I use a low-pass filtering, right? Cut off everything above 8 hertz, and it does me a lot of good in my articulator position estimates. Over here, I can't do that. If I do that, I start throwing away information right and left from the acoustics. This signal over here in the acoustic space is going to be extraordinarily warped. I mean, just think about the transformation from a fricative to a vowel, right? A very small change in the position of the tongue can lead to a huge change in the acoustics. So if I start filtering that out, who knows what I'm throwing away. So I would argue that the articulator space makes it easier to use context information than the acoustic space, where we're often in a situation where we have to predict the next sound just from the current sound instead of being able to filter, and so convolve our sounds with a long window, a sync window, for example. But that's not the only problem with acoustics. Another problem with acoustics that everyone really knows already is that, in fact, the manifold over here, this articulatory manifold, I call it in the acoustic space, is going to change depending on who's speaking, right? People have different vocal tract shapes, so the sounds that come out for the exact same articulator position will differ by speaker. And in fact, they're going to differ by microphone. They're going to differ by how far you are away from the microphone when you talk. And they're going to differ by all kinds of things. And yet we know that people can take those speech sounds and somehow normalize them so that we would still call them the same phoneme afterwards. So you have to say, okay, great, if we could convert this back to articulation, right, that seems like it would be a good thing to do. Right? If we could do that, we would be able to use more context, we could conceivably have more information, because there's maybe more information in the articulator space. We could avoid the problem of a massive number of parameters, most of which are going to be estimated in acoustic noise environment, not actual information about the phonemes. So there are some real potential advantages to doing that. And in fact, there's another advantage that I should mention, that is, has to do with the conditional independence assumption. It's often seen in our acoustic models. Right? Hidden Markov models, for example, often fall into the criticism that the conditional independence constraint is not very realistic. I don't know for sure how realistic it is or not, but I can be pretty sure that the acoustic signal that I produce with a given articulator position is conditionally independent of the other articulator positions I can use and the other acoustics. Essentially, if I know the articulator positions at this time, I can tell you about the sound produced at this time. And knowing the articulator positions at a previous time will not give me that much extra information about the sound I produced at this time. Right? So the conditional independence assumption is likely to hold better for an articulator model than for an acoustic model. So great, if we could get back articulator positions from acoustics, it seems like it might be a good thing. And if I could fly home tomorrow without an airplane just using my arms, that would be a great thing, right? But that's not very convincing unless we talk about whether or not we can actually recover those articulator positions. So that's what I'm going to start talking about now. I actually believe that we can. However, I'm a warped individual, so you should really be watching me to make sure that I don't try to fool you. This is just a summary, though, of some of those reasons. I believe articulation will give us a better conditional independence assumption. We'll have fewer parameters to be learned, and as corollary to that, we should be more robust to the noise environment. It's going to be easier to use the temporal context. We would be able to remove perhaps some speaker information or microphone information, and we may gain information going back to articulator positions from acoustics. And in fact, this one I could talk about a little bit more. It's worth saying to me that by thinking about the speech in terms of these manifolds, we get an idea about differences between the information about what we're saying and the information about who is saying it. I would argue that the information about what we're saying is contained in the articulator motions. If we know your articulator motions, we can say what you said. But that mapping from articulation to acoustics, that's giving you very direct information about who said it. That's telling you about the shape of your vocal tract. Right? So I think that thinking about these things in terms of articulator and acoustic manifolds gives kind of a succinct way of expressing the difference between speaker information and what it is that you're trying to say. So the technique that I'm going to be talking about to invert from acoustics back to articulation is what I call Malcolm. It stands for Maximum Likelihood Continuity Mapping. And this slide shows you essentially what we're going to try to do. Up here again we have the articulator space, where this is some smooth tongue trajectory through that space. This represents the acoustic space. And in Malcolm processing, what we're going to do is first vector quantize the acoustics, which is essentially just breaking this acoustic space into little chunks. And then we're going to follow these green arrows here. We're going to map each vector quantization code down to some position in this new space down here. I call this space a continuity map. And initially, that continuity map is going to have absolutely no relation whatsoever to articulator positions. But I hope and believe that actually after we do a training process, it will recover articulator position. So the steps are we go from articulation to acoustics. These are actually observable. We're not going to use articulation again in this training algorithm. And over here, we're going to try to map down to this space, map VQ codes down to this space. And all we're going to be doing down here is trying to maximize the smoothness of these trajectories. So if I believe that articulator positions have no energy above 8 Hertz, I'm going to find trajectories down in this space that have no energy above 8 Hertz. And in fact, the argument that this will give back articulator positions really has to do with the fact that mappings of that type, which I'm going to argue are mapping from a hyperplane to a hyperplane, have to be affine transformations. So we're really only going to be able to recover the articulator positions within an affine transformation, and that means they could vary by a linear transformation plus a constant. Now, let's make that a bit more concrete. For a one-dimensional signal, like a speech wave, if you were to do an affine transformation of that, you could do two things. You could multiply it by some scalar value because it changes amplitude. Or you could add a DC component, just add some constant to every amplitude. Typically, those kinds of transformations, and that's it for affine transformations, are irrelevant to us, right? We'll take out the DC component anyway, and we'll normalize the amplitude. So, as far as I'm concerned, to a large extent, if we can invert back to within an affine transformation of the articulated positions, we've actually effectively inverted back to articulated positions.
So just let me make sure I follow you. So in the abstract, the problem is that you have a very high dimensional space, let's say 30 or something, and you have a time series in that space. Mm-hmm. And then what you want to do is you want to find a transformation which goes from 30 dimensions to 6 dimensions, 3 dimensions. And what are the constraints now? That the map version of this has to have certain smoothness properties and some low pass properties.
Right, the constraint is the trajectories through this space will have no energy above 8 Hertz or 15 Hertz, or pick a cutoff.
Is there any other constraint? Did you say the mapping has to be affine or not yet?
We find that we recover an affine mapping just by meeting that first constraint. If we make sure that these have no energy above 8 Hertz, right. And in fact, this will end up being an affine transformation.
Okay, so the affine part has to do with the sort of the labeled part of the data where you actually have articulated positions labeled manually or something. But as far as discovering the green arrow is concerned, it's just any mapping which takes you from that space to this space, which
preserves the smoothness, which creates smoothness, in fact. Because in fact, in this space, these trajectories are not smooth. We need to warp this space so they're smooth again.
But where does then, what is it, is there any notion of faithfulness now? Because after all, if I map everything to 0, that's an incredibly smooth mapping. Right?
Yes, that's right. And in fact, that's an affine transformation, I should point out too. But it's a useless one. Yeah, we do put, I hadn't mentioned this before, we do put constraints on it that every dimension in this space is actually used. So for example, another transformation that would be really good is to map things to a line. Right? So we actually force every dimension in this output space to have a variance of 1. Okay? And the different axes are not correlated. So we force it to fill up the space. If we say we're going to find a 2-dimensional representation, and we do. It's a 2-dimensional representation. It's not 0-dimensional, not 1-dimensional. It's really 2.
Okay, so you should tell us more about what the constraints are. On the green axis.
Yeah, you're going to see that pretty soon, actually. I'll talk about how we do it. But essentially, if we see a sequence like this through space, we're going to see a sequence, maybe that's VQ code 1, maybe that's VQ code 2, maybe that's VQ code 3000, that's VQ code 27, whatever. We're going to see those sequences of VQ codes. Each one of those codes is going to get mapped down to a position in this space, and we're going to adjust these arrows so that the positions that we map to fall as close as possible to being on a line or on a trajectory that has no energy above 8 Hertz cutoff range. Yeah.
Why is this problem well posed in the sense that it's unique up to an affine transformation?
That's what I'm going to try to prove to you in a bit. I'm not going to go through the full proof. I'd be glad to go over it afterwards, but I'll try to get across the main ideas of the proof.
And is it clear that that there's a one-to-one map between articulator positions and let's say, perceived utterance, perceived vowels, or perceived sounds?
No. In fact, I would say that, that's not clear. In fact, you picked the examples. I would say that the mapping from articulator positions to consonants is clearer than that mapping from articulator positions to vowels, right? No matter who you are, when you make a T sound, you move your tongue tip up to the alveolar ridge. You know, that's pretty much determined, right? And similarly with N's and D's, but the articulation is very determined in that case. In the research I look at, though, it seems to me that the articulator positions can be more variable for vowels. So when you talk about a vowel in particular, I suspect that we may end up having to combine an acoustic model with an articulatory model to get the best. Because I think it's very possible that acoustic models will work better for vowels, and an articulatory model may well work better for consonants. That's speculation. I don't really know. I'm just guessing. Yeah, no.
Now, when you do that, you have the VQ. Is there any constraints, or do you have any evidence that that actually is EQing on a manifold in that high-dimensional space versus just actually EQing? I mean, do you just do a straight VQ?
I just do a straight VQ. The only evidence I know is that mathematically, if this space has 6 dimensions, and we warp it up into another space, we can't add information. Extra dimensions would be a sign of information being added. This space will absolutely not have any more dimensions than the original space.
Which space? The acoustic space?
Yeah, the acoustic space will have no more dimensions than the articulator space.
But that's your assumption, right?
No, that's just mathematically true. In any case where you have a warping from a space XY to something else, XYZ, right? In the end, you're going to end up with a manifold in that XYZ space. For example, suppose I have a variable x, and I map it to xz or yz, and I do that by saying that y is equal to x cubed and z is equal to the logarithm of x. Right? Now you vary x over all possible positions, and what you're going to find is a trajectory in your two-dimensional space. That's really a one-dimensional manifold in a two-dimensional space. It's never going to be a two-dimensional set of points. Yeah.
Although the input to this transformation might not just be the articulatory space, right? There might be additional dimensions for background noise, for example.
The background noise is what you add. That's what makes you go off the manifold. So that's the point I was trying to make when I talked about robustness. The noise in your room, you know, if someone's mowing the lawn while I talk, you know, my acoustics are going to look a lot more like lawn mowing than me talking.
Right. So the acoustic space might actually have more dimensions than the articulatory space.
But those extra, that's exactly right. But those dimensions are the noise environment. They get information. They have information about the noise environment. And if we stick a high-dimensional Gaussian over there, that means a good portion of the parameters we've estimated are actually estimating information about the noise environment.
Right, but how do you, that gets to my point I was saying, how do you know that you're actually EQing on the manifold? You don't have the output signal right after the articulatory. It's gone through the lip radiation, transmission to a microphone to recording. So you have everything happening. How do you know?
We're going to project it all back on.
Huh?
We're going to project it all back onto a manifold.
Okay, so you're going to assume that the EQ is on a manifold, although...
It won't matter whether it is or not. We're going to take any signal that we get, whether it's VQing off the manifold, and project it onto a manifold. And we're going to approximate that signal by the best that we could have done from an articulator position.
This is a related question. Have you looked at the local linear embedding work? Where
Yes, actually, as a matter of fact, I worked with Sam Royce when he was at Caltech. I thought it was a...
I went to
visit
this issue
him.
where if you have sort of locally linear constraints on the manifold, that's a lower dimensional manifold living in a higher dimensional space, those constraints might essentially address those question.
I think actually it's an excellent point, and I'll talk a little bit about some of the differences between this and local linear embedding now that you brought it up, otherwise I would have skipped it. But yeah, I think Sam Rowe's work is really interesting, tenderloins too. So let me tell you a bit about Malcolm, and we'll try to clear up some of the questions about what we're going to do here. I lied a little bit when I said that we were going to map from each of those VQ code regions down to a single point in this new continuity map. In fact, we're going to try to map down to a probability density function over the articulator map. So for example, the axes in this space mean nothing. I labeled them dimension 1, dimension 2, because originally they're just x, y values and they have no meaning. But I'm going to try, in fact, I'll call any position in this space x. It's a position, right? This is a vector. And we might try to say that this set of concentric circles or ellipses is the set of level curves for a Gaussian, for example. And so this probability density function gives you the probability of a position in the continuity map given a particular vector quantization code or a particular sound type. And in fact, I think you can think about this space as being an infinite set of hidden Markov model states. And we're going to have constraints about what transitions can happen between those states. We're going to say those transitions have to always lie on a smooth path. And this is going to end up being a sort of stochastic mapping between articulation and acoustics. Now granted, at first it's going to have no meaning. But what we're hoping to do is get dimension 1 to have something to do with, say, the tongue body position. And dimension 2 might have something to do with the tongue tip position, etc. So you can see this is kind of a mapping between acoustics and articulation if we succeed at our training. If we succeed at getting this to deal with articulation, right? And given an acoustic signal, a VQ code, you can find the probability of an articulator position. And given any articulator position, you can find the probability of a VQ code, just using this stochastic mapping. So that's what we're working towards, is forcing this to be something like articulation. And initially, when we set up this problem, we're going to make each of those probability density functions just have a random number or a random vector as its mean. Right? So these are just going to be randomly generated. We'll use the identity matrix as covariance matrix for all the Gaussians. So it really is just completely meaningless. It's random. But we're going to pretend, even from step 1, like those distributions are articulator positions, that they are a stochastic mapping between acoustics and articulation. And then when we see sequences of VQ codes, we're going to try to find the most likely path through this space given that sequence of VQ codes. So for example, if we saw the sequence 253, 32, 127, 9, we might try to find a path like this, which is smooth. It has no energy above 8 hertz, for example, but which maximizes the probability of seeing sound type 253, 32, 127, 9. In fact, actually, I flip-flop back and forth here a little bit about whether or not we maximize the probability of the articulator trajectory or the VQ codes. But I'm actually going to be talking more about maximizing the probability of the articulator trajectory right now. So that's the first step. We pretend like this is a mapping from acoustics to articulation, and we find a smooth path through that space that is most likely given the VQ codes.
So just to go back again, I'm just sure I understand. So if there was no constraint on this low-pass nature of it, then the most likely thing would be what? To put them right at the same
Let's go 253, 32, 127, 9.
Okay, you're saying how do we make it smooth?
That's right. We're going to constrain it to be smooth.
But at this point, then you have a mapping which takes the centroid of 253 and maps it to that.
That's
and
right.
you're not going to change that, is that?
We're going to change that on the next step. Actually, we're going to iteratively change the parameters of those Gaussians until those paths are as smooth as we can get them, as likely as possible. So in fact, if we had lots of paths, this would be our point in this case. That's the point, the articulator position associated with sound type 253. If we had lots of paths to this space, then we would have lots of those points associated with sound type 253. And we could look at those points and we could say, how can we increase the probability of that trajectory through the space? Well, clearly we could take this distribution for sound type 253 and move its mean over here somewhere and squish it down a little bit so its covariance matrix match the distribution of points a little bit better. And we could do that for all the rest of the distributions as well. So in fact, what we're going to do is iteratively repeat those two steps. We're going to start out just estimating paths through the space. which I think of as being pretty much analogous to doing a Viterbi search to find the best path to a hidden Markov space with different constraints. Right? And then given those paths, we're going to adjust the probabilities of our Gaussians to increase the probabilities of those paths. It's a little bit different from what we do in the Fourier algorithm, but the idea is the same. So this is sort of the summary in equation language, if you like that. X stands for a path, a trajectory through that space, and we're going to start out giving our set of parameters, phi in this case. We're pretending like those are real, and then we're going to find the X to maximize the probability of this. Right? And here's our conditional dependence assumption. The probability of the current articulator position is dependent on the current code. Right? And then we're going to adjust the phis, adjust the parameters of our Gaussians, to again increase the probability of the paths.
The xt is in one dimensions, or?
It can be in either one dimension or many dimensions. In fact, I'll talk a little bit about those situations here. We're going to do some simulation with our cases. But so far, I've given you some idea about how to maximize a likelihood maybe, but no idea whatsoever as to why it should be that those trajectories that we get through that space actually have anything to do with articulation. In fact, that's going to be the thrust of the talk for a little while now. And the first part of it, you're going to have no problem understanding, right? If I have a trajectory, in this case, say amplitude at time 1, amplitude at time 2, amplitude at time 3. This could be amplitude of a speech signal, for example. I can certainly represent that as a single point in a space which has as its axes the amplitude time 1, amplitude time 2, and time 3, right? This is just a vector. We can represent it like that. What's interesting is that if we look at all of the trajectories through that space which lie on, which have no energy above a cutoff frequency, they lie on a hyperplane in this space. And that's true just because low-pass signals are basically just linear combinations of cosines and sine waves, right? And these are all orthogonal vectors. So if we have signals that are low-pass, they don't go all the way out to the Nyquist frequency, and that means we're going to be relying on some hyperplane in this trajectory space, right? So now we can think about this in terms of trajectories. What we're going to talk about now is mapping from trajectories to trajectories. So we start out with articulator trajectories, and they're all smooth. So they lie on a hyperplane, right? And then we go through some nonlinear mapping. We don't know what it is, but we know that this nonlinear mapping maps these trajectories onto new trajectories. And these, by the way, we can prove to you will not lie on a hyperplane as long as this is nonlinear. So in this case, you may have a mapping from R2 to R3, or from R, however many articulator parameters we have, to R, however many acoustic parameters we have. What Malcolm does is find another function, G. So this mapping we call F, I call F. And this mapping I call G. And G is going to map from this acoustic space back over to here, where these articulator trajectories are smooth again. And so they lie on hyperplanes again. So we're mapping from points on a hyperplane, the points off the hyperplane, back here to points on the hyperplane. In fact, this combined function is really of interest, right? Because it's this combined function G of F that is a mapping from, in this case, R2 to R2. And this composite function is a mapping of points from a hyperplane to a hyperplane, right? That's a guarantee. Now, what's interesting about that is that we have a proof that for most hyperplanes, not for all hyperplanes, but for hyperplanes of interest to us, for example, if you map from all points on a hyperplane to all points on a hyperplane, that mapping is affine. It can't be anything else. No nonlinearity is allowed here. It's got to be affine. So just the very fact that we're going to map from smooth paths down to smooth paths will give us, within an affine transformation of the original signals, regardless of what that transformation from articulation to acoustics is. I say regardless there, and I'm being a little too loose. Actually, there are some constraints on it. If that mapping is many to one, then we can run into problems. And I do not have a proof at this point that we can invert many to one, although I have some examples of some many to one mappings that we actually can recover the articulator position through. In fact, y is equal to x squared is one of those, and that's a pretty severe warping. So while I don't have the complete proof that we can undo any mapping whatsoever right now, I strongly suspect that we're going to be able to prove for a huge class of functions that we can invert them simply by doing this transformation. Now, that though is about mathematics. And mathematics talks about mapping from all points on a hyperplane to all points on a hyperplane. And that's a problem in reality because we will never get to observe all the points on a hyperplane, right? That's every possible articulator trajectory. So in reality, we're going to always have to work from some subset of points on that hyperplane. And that means that, who knows, maybe that subset of points isn't enough to invert the nonlinear mapping. I mean, we're talking about inverting just about any one-to-one nonlinear mapping you can think of here without knowing what it is. So we thought we'd better at least do some simulations to check that out. So in fact, what we did is we produced some one-dimensional signals. This is a lot simpler than the one-dimensional signals that we actually produced. This is just a cosine wave. But our one-dimensional signals had random amounts of energy at different frequencies, all the way up to some cutoff frequency, right? Just randomly chosen. And then we took those one-dimensional signals and warped them by a cubic transformation. Why a cubic transformation? Not particularly a great reason. One of the reasons we chose is because Doug Reynolds and Cortieri did a paper where they tried to model the cubic, the carbon button microphone as a cubic transformation. So we thought it was a good place to start. So a cubic transformation will transform 1 to 1, -1 goes to -1, 0 goes to 0, 1/2 will go to 1/8, and this cosine wave will end up looking something like this over here. And Malcolm is going to take that same cosine wave and try to transform it back over here to some other space. It's really going to try to transform the y-axis of this space, right? So that over here we have a smooth path again. And then what we're going to do is just a correlation. We know what our original paths were exactly because we generated them for this simulation. And we're going to try to do a correlation then between the output of Malcolm and the original paths. So a few more details. We set the cutoff frequency to 5 Hertz in this case. We sampled at 100 samples a second. Each input is the sum of random amounts of frequencies below 5 Hertz. There were 100 input signals and 200 samples per signal, and our input-output function was cubic. We got different results depending on how many vector quantization codes we used to put into Malcolm. But essentially, our correlation went up to 1 very quickly. As a matter of fact, we were able to undo that cubic transformation without the algorithm having any idea that it was a cubic transformation, and without ever giving it any examples of the unwarped input signal. So we should be able to take a speech sound produced by me and unwarp nonlinearities of it, I think. Yeah.
Here's where I'm confused. Suppose your input actually had looked like the result of a cubic transform, and that the transform itself was the identity. Okay. Then the input to Malcolm would have been the same. The output to Malcolm would therefore have also been the same.
Actually,
the
in fact,
output no
we
longer
tried.
have anything like an affine transformation of the input. So I don't understand in what sense you're guaranteeing an affine transformation for a composition of F and G.
We can go over the proof together if we'd like. I don't like to do that during a talk. But in fact, we did do an experiment where we just put the signal in unwarped, vector quantized it, and ran the vector quantization codes through Malcolm. And we ran the signal warped, right, vector quantized it, and ran those vector quantization codes through Malcolm. And we got the same results in both cases. And in fact, in both cases, we would have gotten back to the original unwarped paths.
I'm not asking for proof in the lecture. I'm asking, so my understanding of what you're saying is undoubtedly wrong, because it feels to me like I've got a trivial counterexample to your comment about affine transformation.
Okay, well, what's
So-
the example again?
Okay, so can you go back to the previous slide?
Sure.
I just want to understand how what you're saying is different from
Right.
from my interpretation, to which there seems
This
like
one or the
no,
one?
well, sorry, before that, showing the cubics.
Oh,
Almost, right.
got it.
Okay, so now, F is taking the upper left to the upper right,
Right.
and G is taking that back to the lower left.
That's right.
Okay. Suppose that you replace the upper left with the upper right.
This would not be frequency constrained anymore. This has energy above 5 Hertz, guaranteed.
Because it's
We can't-
cosine.
I see, so you have a constraint on the input.
Right. As a matter of fact, the frequency on this is a cube here of this function. right? And if we take x and cube it, we're essentially going to take the Fourier transform of x and convolve it with itself 3 times. And it's going to have about 3 times the bandwidth of the original signal.
Okay, thanks. That clarifies things, although I'm still interested in talking about that.
Yeah, another detail that may be missed here is that we're going to have, this trajectory here is 1 point on a hyperplane, right? You can find points on that hyperplane that can go through nonlinearity and still meet the frequency constraints. But there's no way you can map every point, every trajectory, down to another trajectory that's smooth without it being an affine transformation.
Okay, much better, thanks.
When you run the simulations, you use 5 hertz as your constraint, and
Right.
so you knew what the real.
We knew exactly what the real data was because we just generated it and we just combined cosines and sines. So we thought we would try this out in 2 dimensions. This is a 2-dimensional transformation to another 2-dimensional space. So over here we show, actually we generated trajectories through this space, but this is the set of all the points that were on those trajectories. And a cubic transformation looks something like this. I like this picture just because it shows that this cubic transformation is actually pretty severe. We're mapping these points onto this space. We're going to vector quantize this space, run those vector quantization code sequences through Malcolm, and try to get back the original trajectories. We tried this at 2 different cutoff frequencies and a variety of different number of vector quantization codes. Again, the correlations were going up pretty fast. I can't remember what the correlations were on these, but it was, this is 0.9, so 0.92, I don't know, we look at it and guess. But we're getting up there pretty high, pretty fast. It worked pretty much the same, whether or not we used 20 hertz cutoff frequency as in the open square line, or a 5 hertz cutoff frequency over here. We did another transformation then. Since Roes in his papers on local linear embedding had done a Swiss roll transformation, we thought we would try something like that too. So essentially, we took this last cubic transformation here and we rolled it up like a newspaper. We did something like this to it. So now it was projected out into a 3-dimensional space. I should point out, by the way, that the technique that Roes used wouldn't have undone that cubic that I just showed you, right? Because it attempts to keep the relative positions of the points, relative distances between the points, approximately constant. So if we took that cubic transformation and stuck it up into a 3-dimensional space, local linear embedding would bring it back down to a 2-dimensional space, but a warped 2-dimensional space. So that's sort of a fundamental difference, I think. The Swiss roll transformation was again inverted. I don't know exactly what the correlations were. It took a little bit longer to get there this time. Essentially, if you have too few vector quantization codes, you're grouping together different portions of the space, portions of the space that aren't connected. So we have to get to a certain number of EQ codes before we get a good invert, but then we get it. And we also said to ourselves, well, in reality, we're never going to get a signal that has absolutely no energy above 8 hertz cutoff frequency or whatever, so we better try out somewhere we let the signal have more energy. So we tried out a frequency mismatch experiment. In this case, we started out with random signals, these random smooth paths, right, that had energy up to 16 hertz. We warped them, and then we ran Malcolm on them, but we told Malcolm that the signal had no energy above 8 hertz, so we lied. And then what we did was compare the output of Malcolm to the output of this original signal that went through a linear filter, so that it had no energy above 8 hertz. And in fact, we did that lying to Malcolm in various ways. We sometimes use a signal that had no energy above 16 hertz. Sometimes we use a signal that had no energy above 15 hertz, or no energy above 12 hertz or 10 hertz, right? And that's what's shown here. And these are the correlations between the output of Malcolm and the random smooth paths. Right? And as you can see, first of all, the y-axis starts out at 0.90, so all these correlations are fairly high. I think the lowest one we got was about 0.95. And we just got these before I came out here, too. But as we lie more, so when the signal actually had energy up to 16 hertz, and we told Malcolm it had energy to 8, we did a little bit worse than when we told Malcolm that the signal had energy at 8 hertz and it actually had energy at 10. Right? So we can get better if we don't lie. But we didn't lose that much. I mean, the correlation over here was greater than 0.99 something. And the correlation over here is still about 0.95 something. I sort of recall 0.95, but I'm not sure about the exact numbers. So even when our assumptions aren't exactly met, it still seems to be able to invert this relatively severe warping, right? That was done with one-dimensional signals, by the way. We also tried this out on articulating data. So we actually had a Swedish speaker produce vowel-to-vowel transitions. And while he did that, we measured the position of little pellets we stuck to his tongue, jaw, and lips, right? So we had the acoustics recorded at the same time that we measured his tongue, jaw, and lip positions. And we vector quantized the acoustic signal. We did the Malcolm mapping on vector quantization codes. We did not use the articulator positions in any way for that. And we got back estimates of articulator positions. And we said, well, I wonder if those have anything to do with the actual articulator positions. And it turned out that they did have something to do with that. As a matter of fact, we saw some very high correlations. So you should pay attention to this dark line right now. Down here on the x-axis, we showed the tongue rear x position correlation between our Malcolm estimate and the actual tongue rear x position. Tongue rear y, tongue body x, tongue body y, up to tongue tip x and y. And those are just pellets that go from back here somewhere to up here somewhere. Yeah.
So this involves some mapping of the axes of your reconstruction onto the axes shown on the x-axis.
That's right. As a matter of fact, we used something called Procrusteus analysis to do an orthogonal rotation, reflection, translation, and scaling to make these things match up.
I see. So that introduces some additional degrees of freedom in the evaluation. I don't know how many data points are behind each one of the correlations.
A few thousand.
Okay, right. So additional degrees of freedom are
yeah, it's not going to be a big deal. In fact, we're going to compare it up here to the principal components, where we just take articulator positions, project them down into the principal components space, and then back up to articulation. So we've never used acoustics at all in that transformation. In some sense, it's as good as you can ever expect to do with 4 dimensions, right? And so that's with this dashed line up here. That's sort of our comparison here. We're going to see how well we can do it compared to how well you can ever expect to do.
So and it's really interesting that you actually track that.
Did we get what?
That you actually track that. That the lower line had the same shape as the upper line.
Yeah, and it doesn't for some of them. The best ones we got were like what is that, tongue body Y and tongue dorsum Y. So really about the middle of the tongue, how far up and down it's going. And that's very important, obviously, as a critical articulator for vowel production, which is what we were studying here. And even the X position for hitting back correlations was at about 0.94 or so. The jaw X position is what we did the worst on. That's actually sort of irrelevant. I put it there so you can see reality, but really the jaw doesn't move very much in this direction when we talk. The motion in this direction for these pellets was about the order of the error that we can expect on pellet measurements. So this doesn't really mean much jaw wide. We got back pretty well. About
But you're still getting almost 80% of it.
Yeah. It's probably because the estimates for the error in the Emma position coils are made by human beings. They say, well, suppose this happens and this happens, then we can guess this error is about this much. So we don't know really what the error is, but probably they were overestimating it. And probably that's why we get about 0.8 there, is my guess. Now, you might think, okay, well, at least I think we can give back articulator positions with some degree of accuracy, right? We should start using that as input to a speech recognizer. I'd be a little cautious about that because speech recognizer systems that we have right now do in fact have this conditional independence assumption. And boy, articulator trajectories do not meet your conditional independence assumption. They are very smooth. They have no energy above 8 hertz. So you can definitely use the previous codes to get information about your current code, right? So I think you have to be a little bit careful about that. Instead, I would suggest that we do maybe put more Gaussians over this articulator space, this continuity map. Maybe something like this to give you the probability of a position in this space given a certain phoneme, which I've characterized as F here because P was already taken. So for example, if the phoneme was buh, what's the probability of different articulator positions in this space? And if you did that for all the different phonemes, then you could output a table like this. At each time, you could output the probability that that signal was a puff, the probability it was a buff, probability it was a muh, e, ah, oo, etc. for all the different phonemes, and this row would guarantee to add up to 1. Right? That's a nice thing for a probability to do. We're not talking about the height of a probability density function here. We're talking about real probabilities. You wouldn't have to do that. You could also output something like this, where you try to output articulatory features like was it voiced or unvoiced. This actually has some speed advantages because calculating the probability of something given only 2 distributions is just faster than calculating given 40 distributions. Once you had done that, and that is, by the way, what we call conditional observable Malcolm, which means in that case you're going to take vector quantization codes and try to find the conditional probability of phonemes given those codes. So you have one that's conditional upon the other observable. And in fact, you shouldn't just generate the Malcolm space first and lay down those distributions. In fact, you should try to maximize the probability of the correct phoneme, and you can actually do that. You can adjust the positions of the distributions given the VQ codes, as well as the positions of the distributions given the phonemes, to maximize the probability of the correct phoneme. So we have an algorithm, it's simple, gradient descent type of thing, that will let you do that. And once you've done that, there's actually a simple way to use the current trellis models, the language models, to combine those probabilities for phonemes that you just got out with language models like we use right now, or word models to give you the probability of phonemes given words. We can combine those with the probability of these phonemes given co-Malcolm, use just a slightly modified forward algorithm, and you can get back an estimate of the probability of a word given the acoustics. So I think that we can actually use articulator information without throwing away a good portion of the trellis model work that we've done already. I don't know whether that's the optimal thing to do, to be honest, but I don't know that it's not the optimal thing to do either. And until we think more about how you might try to use articulator positions for recognition, it seems like not a bad idea. Talked a little bit longer than I thought I would. My conclusions are that articulator positions should be recovered from acoustics because they're going to be more robust in the noise environment. They're going to be easier to use with interpolation schemes, and so use context to get rid of noise. They're going to be invariant to microphone nonlinearities. Microphone nonlinearities is just one more nonlinearity on top of that mapping for different speakers. I think they're going to be more robust to speaker differences. I think they're going to allow better modeling the conditional dependence of speech signals. Hopefully, we'll eventually be able to use some of this articulator type of data to build up or to use some of what we know about articulation to help us out with the recognition. So right now, we use a statistical model, for example, to try to recognize given these articulator positions. But maybe someday when we know a little bit more about articulation and how to recognize speech given articulation, we might change our model around. I think it gives us opportunities for improvement in the future. But I think it's still important that we could do this in conjunction with the standard trellis models. So in the relatively short term, we could build this into a speech recognition system. It may work, it may not. I can't predict that. But I think we could do it. There's actually one more point that I want to make. I don't see any hands up right now. This is more historical than anything. Periodically, people want to hear that something you're doing is biologically motivated. I don't know that I buy into that very much. But this was biologically motivated. I started out as a psychologist, and I went to this talk about some work that Michael Merznick had done. And it turns out that you have in your brain, and so do monkeys, what's called a somatosensory homunculus. So you can actually draw a picture of your hand on your brain. And when you poke the finger at a certain point, then that picture, having to do with that finger, would light up, in essence, in your brain. Right? And in fact, Michael Merznick found that if you poke that finger a lot there, then over time, that section of the brain would expand a lot. And what was even cooler was that this guy actually took a nerve from the pinky of a monkey and he implanted it in the thumb of a monkey. And of course, when you poke that, the pinky part of the brain lights up for a little less than a month. A month later, the thumb part of the brain lights up when you poke that. Well, how did the brain know that you just moved around its nerves, right? And I thought that was fascinating. The hypothesis that they came up with is that they never actually touch one nerve at a time. When you put your thumb down on the table, you touch a bunch of nerves. All your brain has to do is say, hey, look, these two nerves lit up at the same time. Let's represent them close together in the brain. And if I do that, and do this over lots of different touches, then pretty soon, those nerves that are close together on your hand are going to be represented by nearby points in the brain, right? And that was actually the inspiration for the whole idea. At the time I was reading about the motor theory of speech and psychology, and I thought, you know what? As my tongue moves around in my mouth, if I take two sounds that occur close together in time, I know that my tongue didn't move very far between those sounds. All I have to do is say, okay, if I see two sounds that occur close together in time, let's represent them by nearby locations in a space. And that became the continuity map. That wasn't actually good enough. When we did the correlations between articulator positions and the estimated articulator positions using our first attempts like that, and that is actually very similar to the kind of stuff that Royce was doing with local linear embedding, we got correlations of maybe 0.7, 0.75. When we put in the smoothest constraint, those correlations go to 0.97. So we like the smoothest constraint a lot, and now finally, I actually did work with articulation several years back, but now that I understand that a mapping from a hyperplane to a hyperplane has to be affine, now I finally understand why our correlations went up so high. It's not just that we're going to get back a topological map if we map from a hyperplane to a hyperplane. We're going to get back an affine transformation of the original. And so I believe we can actually recover articulator positions from acoustics even without ever training on articulator data. That's it. Yeah. Sure. Oh, I thought you were raising it.
Yeah, actually, it's only invariant up to an affine transformation if the mapping is onto, isn't it?
Yeah, that's right. Actually, we can, and in fact, it doesn't work always in that case either. Let's suppose that we have this hyperplane. So we have x, y, and y is equal to x, right? That's a hyperplane in this space. Right? If we transform the x and y variables by x squared, right, so now we have x prime is equal to x squared, and y prime is equal to y squared. That's still going to lie on the hyperplane and is a nonlinear transformation, right? So for some hyperplanes, in fact, we can't be sure that we're going to be getting back an affine transformation. However, if we move that a little bit off of that axis, a little bit away from x equals y or y equals x, I guess it doesn't matter how I say that, then we can all of a sudden recover within affine transformation again. And it's kind of cool that, in fact, for speech, these bandpass signals that we're interested in lie on hyperplanes that we can recover. So, you know, the proof does have some caveats and some details to it. And I'd be more than happy to go over that as well as I can once I'm sitting down and can think about things more slowly. I'm not very good at math. If it wasn't related, Gerbert's helping me out on this, but we've never gotten this far. Yes.
I had a question about your whole experimental paradigm. I didn't quite understand it.
Okay.
So it looked like you would, for example, in the simulation experiment, you would take a signal, say a cosine or something,
Right.
and then you would put it through some nonlinear matrix F. And then you actually know the ground truth, you know what the original lower dimensional signal is. And in your case, you always had either 1 to 1 or 2 to 2, but you could also have done 1 to 3 or something.
Yes, well, in fact, we did 2 to 3.
Right.
That was that Swiss
Right.
roll transformation.
And then you take the data and you get Malcolm to try to figure out the lower dimensional mapping. And then you measure the correlation between this and the original signal by allowing, I guess, the most forgiving affine transform.
We do a correlation. Correlation allows for those transformations.
Right, basically it allows...
Because we get to remove the mean, that
Right.
removes the DC component, and it doesn't worry at all about the standard. So
Right.
correlation gets rid of that.
So, I guess one of the things, if you wanted to use this in speech recognition, I think one of the things I would want to do is a different experiment where you actually go ahead and estimate the transformation, which would take the Malcolm output back to the original space on one data set,
Yeah.
and then measure the estimation error on another data set. Because one of the things that bothers me is that you are sort of using the most, like, correlation is a very forgiving measure.
Oh yeah, well, we can generate thousands of these, in these simulations, right? So it is true that you have 2 extra degrees of freedom, right? When you do a correlation, you've got your DC component and your magnitude, right? Your scaling. Well, we do this with 200 signals, 100 sample sets, so we got thousands. In fact, in some cases, we've done it with, a couple thousand signals, right? The more signals, the better. Eventually those 2 free parameters we've got just are relatively irrelevant. I mean, you're used to thinking about doing the training test set separately because in most cases we use these very strong nonlinear mappings, right? A neural network, for example, is trained on the input and then tested on some new output. A neural network can approximate any function. Well, correlation can't approximate any function, right? It's much more severe than the multi-parameter system that you usually use. I would have no problem testing it out on a completely separate set of data. I think it would work fine. Can't prove it.
No, more than a separate set of data, instead of just looking at correlation, you'll actually be able to measure some kind of trajectory as mean square. I don't know what would be an appropriate measure.
Yeah,
because in case of the speech signal, you really want to measure detection error.
Well, yeah, you wouldn't want to do mean square error because...
Well, whatever, some appropriate metric of the actual...
I think actually correlation is the most appropriate metric for comparing...
And because you said earlier that you recover articulatory position within a couple of millimeters.
Yes, I see. When we actually, yeah, now in that case, when people are doing experiments like that, yes, we do test on a testing set. That's different than this, right? In that case, for example, we've got to quantize acoustics. We would just find the average. We go to our measured data set, right? We find the average articulator position associated with that vector quantization code, and we use that as our estimate of the articulator position every time we saw that VQ code. And then we would go to a different set of data. We'd use the same VQ code book, but we would use those same articulator estimates that we got from our first set of data, and we would compare to see how well the estimated articulator positions fit with the actual articulator positions. And we saw errors of about 1 millimeter or 1.5 millimeter, something like that.
So there was no Malcolm business in that?
Not in that, no, not at all. In this case, we only had correlations. Yeah, that,
So maybe a little bit along those same lines Sanjeev was asking about, what is the correlation coefficient, like in this 1D example, if you did nothing to the cubic?
goes down to about 0.7, something like that, 0.7, 0.8. I can't remember the
It was
truth.
around 0.8.
0.7,
About
0.8.
0.7.
Could be
So
0.7.
that would be
I could
the
find
number.
out and I could send you the, yeah, I mean, yeah, it's a really, really good question. We did get those and I don't have them off the top of my head. I can find them and then, be happy to send
Yeah,
them.
because I guess the correlation, I'm not familiar with looking at that a lot, so it's partly my naivete, but part of it is I don't know what to gauge it relative to. In other words,
Yeah.
90 sound good, but I don't know what is it relative to.
Well,
So if
in
it's
almost,
relative to 70,
yeah.
is that a significant gain? Is that not? I don't know what's random. 0.5.
Right, I mean, it's a really good point. People use correlation all the time. In fact, some people will use R squared instead of R. Typically, when people present these things, they use R as the measure. So that's what we did here. But yeah, I don't completely know either what's good and what's bad. I do know that in almost every case, when you see a correlation about 0.995, people consider it pretty good, right? But whether that's twice as good or just a little bit better than 0.8, I don't know. Right? Yeah, there's some nonlinear function going on there too.
You learn that too.
Yeah, and I don't know really how to get at that better than that. I can tell you though. In fact, I could probably show you a demonstration of the actual and estimated articulator positions and go along with 0.97, and you'll look at them and you'll see these points going like this. Yeah, I have it here on my computer, and so you get a feel just from looking at it. The 0.97 is pretty good, right? That's a good correlation. 0.99 is a really good correlation. So now that's the best way I can think of to give you an idea. Yeah.
Jim, maybe we're making this one point on the graph where you were showing various bandwidths, but do you look at this, rather than saying this transformation is correct within an affine transform, is a different way to look at it that essentially you have the affine components and the non-affine components, and the non-affine components are reduced as a function of the bandwidth. And when you're getting to be have very small bandwidths, essentially the non-affine components of the transformation drop are become negligible. Is that how you would look at it, or do you really look at it as you're saying, like an almost binary case where at some bandwidth it's fine?
Well, given an infinite amount of data, if we manage to do this transformation, it's affine, right? Given less than infinite amount of data, which is what we've really got, there can be some nonlinearity in the working. I don't know how to think about it when I start talking about what happens when we lie to Malcolm. I mean, that's part of why I did the simulation. I don't have a proof that it should work. I suspect what's going on is that we're just taking a signal and projecting it onto a hyperplane in that case. That's how I usually think of it, but it's certainly not clear from the mathematics that that's exactly what we're doing, not to me. I don't know much more than that. I'm afraid that's about all I can tell you. I don't know how to think about it. I think, given that it worked, that we can probably find a proof that it's going to work. Right? But I certainly do not have proof like that.
Because if what I said isn't true, then I would ask, well, how large bandwidth can you go up to?
Yeah, now I do know that when, in some cases where we've told Malcolm to see that the signal had no energy above 8 hertz, and we actually gave this signal up to 4 hertz, right? And there it didn't do very well at all, right? Because, in fact, you can square a signal, right, that has no energy up to above 4 hertz, and it still has no energy above 8 hertz, right? Again, we take the signal and the Fourier transform that has no energy above 4 hertz, we multiply those things, which is convolving in the Fourier space, and we double the bandwidth. So you have to be a little careful, right? When you, presumably, if you lie to Malcolm too much, it's going to completely fail, right? And that was a case where it certainly didn't do very well. So you can mess up a little bit in both directions because it would do pretty good. You know, we would tell it that the signal had no energy above 8 hertz and actually had energy up to 5. Couldn't double it anymore. So if you treat every nonlinear transformation as a Taylor series approximation, right, ignore the linear term, start looking at the higher order things, square comes up first. A squaring in your transformation means you're going to double bandwidth. So I think that if we're within a doubling of bandwidth, we're probably okay, but I don't know for sure. I'll be around. Is there more questions?